Okay, guys. So types of matrix. We need to know different type of matrix. So you can see this screen in your screen, right? Handout 2.1 and 2.2.
Yes,
Okay.
sir.
All right. Good. So let's continue. Column matrix or vector. So if there is only one column, there may be different, rows, maybe 2, 1, 2, 3. It could be anything, but if there is only one column, then we call it column matrix, or we can just call it vector, in the sense that if you draw this figure, let's say, if you draw this 1 and 3, 1 and minus 3, what we get here is that x is 1, y is negative 3, means 1, 2, 3. So that is the point, and if you join that point here like this, you're going to get a vector. It has a direction and as well as the length, magnitude. Okay, so you can say this as a vector or just a column matrix. And row matrix means if there is only one row. Column may be different, but row is only one. We call it row matrix. Rectangular matrix means it's a rectangular. So number of, in this case, number of rows is 2 and number of column is 3. So this is the size of the matrix here is 2 by 3. So it's this type of matrix are called rectangular matrix. Square matrix, by by this word, you already figure out what is a square matrix is, right? So the number of rows and number of columns are equal. For example, in this case, the first one is 2 by 2 matrix. The second one is 3 by 3 matrix. So they are a square matrix. Diagonal matrix means only the diagonal are non-zero. Okay. And every other except the diagonal we don't care. So except the diagonal, everything is 0. We call it diagonal matrix. Unit or identity matrix. So identity matrix or unit matrix is actually the diagonal matrix whose diagonals are 1. As you can see, if you draw the diagonal there, all these diagonals are 1, but every other are 0. That is called, unit matrix. So this is unit matrix in 2 by 2. This is unit matrix in 3 by 3. Null matrix or zero matrix means if all the elements in the matrix are 0, then we call it zero matrix or null matrix. Okay, null means 0, nothing. Well, not nothing, but 0. Triangular matrix. There are two kinds of triangular matrix. One is upper triangular matrix, another is lower triangular matrix. Okay, so upper triangular means the lower part, if you just draw the diagonal, then lower parts are all 0, then we call it upper triangular. So in the upper part, it could be 0 or it could be number, doesn't matter, but just make sure that everything below that diagonal is 0. We call it upper triangular matrix. Okay, so if everything above the diagonal is 0, then we call it lower triangular. In the lower part, it could be 0 or non-zero number. Okay, it could be anything, but the upper part is all 0. In that case, we call it lower triangular matrix. Okay, so now the question is, how do we find the addition and subtraction of the matrix? So let's look at very quickly. In order for addition and subtraction to exist, the size of the matrix must be exactly same. Keep that in mind. So for addition and subtraction, size must be the same. Okay, must be equal or same or equal. For example, let's look at a plus b. We need to find a is given, b is given, and c is given. We need to find a plus b and a plus c. So a plus b. A is 2 by 3 size and B is also 2 by 3 size. As you can see, the size are equal. Okay, they are same size. So we can find the sum of A and B. So let's find A and B. A is 4, -1, 0, 3, 5, 2, plus B is 1, 3, 1, 5, and 1, 7. So how do we find that? Well, we'll add component wise. Okay, the first component, first row, first column 4, so you'll get 4 plus, and here first row and first column is 1, so 4 plus 1. Second component will be 0 plus 1, third one 5 plus 1, and this one is -1 plus 3, and this one is 3 plus 5, and 2 plus 7. So all together you're going to get 5, 1, 6, and 2, 8, and 9. Okay, that is the sum of A plus B. Now A plus C, let us look at what is A plus C. Now my question is the size same? A is 2 by 3 and C is 2 by 2. Because size are not equal, right? The size are not the same. So if size are not the same, then addition does not exist, okay? So addition does not exist because size of A and C are not the same. Okay, so that's how we add and subtract, the same idea. We just add and subtract component wise. Here is a theorem. Let A, B, and C be matrix of the same size. Matrix of the same size, keep that in mind. And let R and S be scalar. Then A plus B will be B plus is equal to B plus A. We call it commutative property. Okay, you can switch the position of that and you'll get the same value. If I do this A plus B and if I do B plus A, as you can see clearly, it must be the same, right? We're just adding the numbers. A plus B plus C and A plus B plus C. So see that this one is one group. First, we need to do the operation inside the parentheses. So if we add A plus B first and then add C, if we add B plus C first and then add A, then the result will be the same. Okay. If we add 0 to A, then we get A. Same. So part B is actually the associative property of addition. We call it associative property. The first one is commutative. The second one is associative. Third one is, we call it identity property of addition. So when you add 0 to any matrix, then you get the same matrix. Okay. If we multiply by any scalar, part D, as you can see, R, A plus B, R, A plus RB, they are equal. Or you can do this. So multiplication by scalar. Okay. And this property also holds true. So these are basic, properties of matrices, and they holds true. Now with this, I think you will not have any issue with addition and subtraction. It just add and subtract component wise. Now matrix multiplication is a little bit interesting topic, so we'll work on that now. Okay, how do we multiply two matrices? So if A is an m by n matrix and if B is an n by p matrix with column B1 up to BP, then the product AB is m by p matrix whose columns are AB1, ABP. That is, we can write AB equals this way. Now, by just reading the definition, it may not make sense if you have not done this matrix before, but with example, I think it will be clear, okay? Even if you don't understand by reading the definition, don't worry. So we will be working on the on the examples. All right. So with the examples, I think everyone will be okay with that. Before I do this example 2, I want to move further here. Okay, we will skip example 2 and 3, and we just want to look at this first example, this one. It's a real world applications of multiplication. I want you to read this at these lines. It gives you a background, the historical, you know, historical note about the matrix multiplication. So the method of multiplication of matrices is not as intuitive and may seem strange sometimes. Although this method is extremely useful in many mathematical applications, not only mathematical, but in economics and business and, in science, engineering. So uh, it seems strange, but the application is enormous, okay? Matrix multiplication was introduced by an English mathematician named Arthur Cayley. And let's look at this example. A car dealer sells 4 models type A, B, C, D. There are 4 different type of model of cars. On a given week, this dealer sold 10 cars of model A, 5 cars of model B, and 8 cars of model C, and 3 cars of model D. The selling price of each automobiles are respectively given this. These are the selling price, okay, for that particular model, each of the particular model. Now represent the data using matrix and use the matrix multiplication to find the total revenue. Okay, how do we do that? Well, you can say this, on one side, revenue. How do we write the revenue is number of models of car. You can write this side, and here you can list this price, because quantity multiplied by price gives us the total revenue, right? Quantity, number of model of cars, number of cars times price. So in order to express this in matrix, how you can write down is model is type A, B, C, D, and then the price will be price, let's say P1, let's say this one is P1, P2, P3, P4. Okay, if we multiply this, we should be getting the result. So let us write A. How many of A? How many of the model, A model? 10 cars, right? How many of B? 8. How many of C? Oh, I messed up. So B is 5. C is 8 and D is 3. And now the price for each of them is the first price is 12,500. Second price per car is 11,800. Third one is 15,900, and the fourth one is 25,300. All right. Now we multiply this because quantity, number of model of car times price. So how do we multiply that? Well, we multiply this times this. So 10 times 12500. You might, some of you might be wondering, oh, that's so simple. Why you are making life difficult by putting that in matrix? But the idea is, this can be expressed in matrix, and from this one we will learn the matrix multiplication. That is the idea. Okay, so this multiplied by this plus 5 multiplied by 11,800 plus 8 multiplied by 15,900 plus 3 multiplied by, and if you multiply all, what do you get? Anybody has any idea?
Krishna, why we write this one in a row and the other one in a column?
Okay, uh, because we are trying to learn the matrix multiplication, and we will discuss that in a minute. Why so? Okay, so what do you get if you add all of them? Okay, let me see. Some of you have already calculated there. So 38,000, no, 387,200. 387,200. Okay, now notice one very important thing. This matrix is 1 by 4. Okay, row 1, always the size of the matrix is row by column. This is 1 by 4 size. And this matrix is 4 by 1 size, right? Because there are 4 rows, this horizontal is row and vertical is column. So there is one horizontal, one row, and there are 1, 2, 3, 4 vertical for the first part, 1 by 4 matrix. That is the size of this matrix. Or you can say here. So this is 1 by 4 matrix. This is 4 by 1 matrix. Now, one very important point to remember here. Okay, listen very carefully. Now, the matrix multiplication possible because this one and this one are equal. Okay, the column of the first and the row of the second, if they are equal, then only the matrix multiplication exists. So there is a theorem. We'll talk about that theorem after some time, but just keep that in mind. They must be equal. Otherwise, we cannot multiply these two matrices. Now, what is the resulting matrix? The resulting matrix will be this by this, so that 1 by 1. So the resulting matrix must be 1 by 1. That's what we notice here, as you can see. So this is 1 by 1. There is only one item, right? So this one row, one column. Very important. So this gun, so the remaining is 1 by 1. That's how we can calculate the matrix. One important thing to remember is that first row, we take a first row and multiply with the first column. In the same way, if there are other, two columns, then we multiply the first row with the second column as well. Okay, we'll do that. Let's look at next example. I think next example will help us to understand a little bit further. Okay, guys, I want you to change this into matrix multiplication. I know you can use your common sense and find the total answer, but our goal is to develop, because in the computer programming, when you have, let's say, hundreds of variables, hundreds of variables, now you have hundreds of equations, hundreds of like rows and columns, then our common sense will be really difficult. And once we change this into matrix, then now we can solve it easily. And this kind of matrix multiplication is extremely important in computer programming. If you have done any computer programming, I think you know the importance of this. Okay, so let's look at that. Here, I suggest try to write down this in a matrix form, guys. I'll give you a little hint, and please try to write this in a matrix form. So this side, okay, let me read the question. What is that first? Suppose you have a business. Oh, you are a business owner. There is something missing. Okay, there is a typo. You are a business owner. Suppose you are a business owner and sell clothing. The following represents the number of items sold and the cost for each item. Use matrix operation to determine the total revenue over the 2 days period. Okay, there are two things given. One is unit price of each item. Okay, and then we are given quantity sold, quantity, how do I write in short? Let's say quantity sold for each item on Monday. There are 2 days on Monday, and another is what day? Tuesday. Okay. Now let us write down that in a matrix form. So the unit price is $10 for the first type, $15 for the second type, $20 for the third type. Now on Monday, how many sorts were able to sold? 3. First type 3, second type
4.
4, hat, and the third item is 1. And on Tuesday, 4, 2, and 3. Now my question is, can multiplication exist in this case? Because in order to find the total price, the revenue, then price multiplied by quantity gives you revenue. We know that. That's just a common sense. Price times quantity. So is the matrix multiplication exist in this case? What is the size of this? Size of the matrix is 1 by 3.
Manjinder, oh chapter.
Hello, sir. Who is this? Okay. Do you think the matrix multiplication exists? Okay. Yes. Sandeep. Yes. Grace. Yes. Min. Thea. Yes. Okay. Let's check. So the size is 1 by 3 and the size is here 3 by 2. So as you can see, this one, the column, this part and this part are equal. Yes, the matrix multiplication exists. And what is the resulting part? If you multiply this, your matrix size will be size will be 1 by 2. Okay, let us multiply that here. Okay, I just want to copy that now. The first one is 10, 15, and 20. And the second matrix we have is 3, 4, 1, and 4, 2, 3. Now, how do we do that? Well, the first row we multiply with the first column. So the first thing you'll get is 10 times 3, okay, plus 15 times 4 plus okay, hold a second. So this will be this one, and we write that way. Yes, 10 times 3 plus 15 times 4 plus 20 times 1. Okay, that first one is done. Now the second one, the row and with the column. Here we'll multiply 10 times 4 plus 15 times 2 plus 20 times 3. So that will be our resulting matrix, okay? So if I do that, then what do I get? What is the first one? Is that 110? Second one is
130.
130, okay. So on day Monday, the total revenue is 110. On Tuesday, the total revenue is 130. So if you want to find the total revenue, Monday and Tuesday you need to add. But what we found here is that Tuesday revenue is this, I mean Monday revenue is this, Tuesday revenue is that, okay, Monday and Tuesday. Okay, now as expected, the result should be 1 row and 2 column, and this size is, as you can see, the size is 1 row, and because that 1 horizontal and 2 vertical, so 1 by 2 size. That's how we multiply. Okay, I can write this in a little bit different form like this: 10, 15, 20, and multiply 3, 4, 1. Okay, and then you multiply that, and in another one, 10, 15, 20, and then multiply 4, 2, 3. You can write that way too as a matrix. Okay, so we multiply this with this, write it down here, and this with that right down there. So that's how we, multiplication exists. Now let's go back to example 2 and let's practice here. First of all, this is 2 by 2 size, and this size is 2 by 3. Does the multiplication exist? Yes, right? So the resulting matrix should be 2 by 3. Okay, so do you want to try this? Now you can do this way too. Like how we did here is that this one is, let's say, let me denote that by B1, this one by B2, this one by B3. So how we did that earlier is that in order to multiply this, we can now AB is AB1. You can write this way. Maybe B is, let's say, B1, B2, B3. Okay, I just write that column. So A, now you can write AB1, AB2, AB3. So that will be the result. So what is AB1? Let us calculate what is AB1. AB1 will be, A is 2n1, 3n minus 5, and B1 is 4n1. If you multiply, what do you get? Let's see. The row with column. Remember that, row with column. Remember, this is 2 by 2, this is 2 by 1, so the resulting matrix should be 2 by 1. So row with column, 2 times 4 plus 3 times 1. We are done with that. Any question so far? Now the second row with the same column. So 1 times 4 plus minus 5 times 1. That will be the resulting one. So as you can see, it is clearly, that will be 11, and that will be how much? -1. And as expected, this should be 2 by 1. So we got that AB1. Now AB2. In the same way, you can find this AB2. And B2 is 3, and as you can see, B2 is 3 and -2. And multiply in the same way. Row with column. So 2 times 3 is 6. Minus 2 times 3 is 6. So we are done with first row with first column, and now the second row. 1 times 3 is 3, and this, -5 times -2 is +10. So basically what we got here is 0 and 13. And now AB3, let us calculate that. A is 2, 3, 1 minus 5. And B3 is 6 and 3, as we know from here, 6 and 3. And now always row with column. So 2 times 6 is 12. Row with column. 3 times 3 is 9. Row with column. So 1 times 6 is 6. Minus 5 times 3 is 15. So we got 12 plus 9 is that 21? And 6 minus 15 is minus 9. So we just now, AB1, we got the value, 11 and negative 1. Let me just write it down. So AB1 is 11 and negative 1. Okay, so 11 and negative 1. AB2 is 0 and 13. And the last one is 21 and negative 9. This is one way of doing. I call it long way, long method. Any questions so far?
So can we do also as you first teach, like or is this method is compulsory?
Say again.
So can we do this by another method also?
Yes, yes, there is a short method I'm going to show you in a minute. Okay, this is, but technically it is the same thing, but we combine all of these steps together so that it looks short. But as a matter of fact, we're going to do all of these things, but it looks short.
We need to show all calculations.
No. Okay, method 2. For the same thing, I don't want to spend a lot of time like that. At the beginning, if you go for that way, I think it makes more sense and it's less confusing. But once you are familiar with the matrix multiplication, then you don't have to go that route. It takes a lot of time actually. So now the second method is, okay, A, B. I just write down A and B here, which is A is 2, 3, 1, negative 5. And B is 4, 3, 6, 1 minus 2, 3. And what we already know is that we take a row from this one and multiply with a column. Okay, let's do that. Row is 2 times 4. 2 times 4 plus 3 times 5. No, 3 times 1, sorry. 3 times 1, okay? Row with column. So we take this row here, multiply with column, this one. Okay, we got that. Now the same row with column. Let's take a second column. So 2 times 3, this row, and now this column. 2 times 3 plus 3 times negative 2. So we are done with first row and second column. Now we'll do first row with third column and write it down here. So 2 times 6 plus 3 times 3. So we are done with first row. Okay, we multiply first row with first column and second column and third column. We are done. Now let us take the second row. So the second row is, now we consider that and we multiply the same way as we did before. So 1 times 4, 1 times 4, and plus minus 5 times 1. Okay. Second row with first column. Now second row with second column. So that's going to give me 1 times 3 plus minus 5 times negative 2. Now this with the third column. So that's going to give me 1 times 6 plus minus 5 times 3. and I should get the answer now. The first one will be 8 plus 3 is 11. This, and then this one is 6 and 6, it will be 0, negative 6, positive 6. This will be 12 plus 9 is 21. And this one should be 4 and negative 5 will be negative 1. And this will be 10 plus 3, 13. And this would be negative 9. Okay. So you can follow any one of these methods. Which one you like, by the way?
Second one.
Second one.
Second one? Okay, let me see. If all of you want to use the second one,
Second
then
one.
second one, okay. It saves a little bit of a time, right? Second one, okay. Yeah, few people like first one, but most of you like second one. Okay, I think I'm gonna follow the second method. And a lot of time you can do these calculation in your head, by the way. You don't have to show all of these as well. You can just directly write 2 times 4 is 8, 3 times 1 is 3, so 8 plus 3 is 11. So you can go from here directly to there if you like. But at the beginning, you know, to make sure that you are familiar with the matrix multiplication, I suggest write down all of these like just the way that I did. But after a few problems, then I think you can go from here directly to that. Okay, example 3, I want you to try this, then we take a break after this. Okay, try this. I'll give you 5 minutes for this, and then we take a 10-minute break. So we'll meet at okay, so this AB 28 minus 40 negative 45 to negative 4, that's one is correct. Now you may want to try BA, reversing the order. And as you can see, B is 3 by 2 matrix, A is 2 by 3 matrix. And since these two are equal, column of the first and row of the second are equal, multiplication exists. And the result will be 3 by 3 matrix. And I'm just waiting for your answer.
So, sir, I've got, I don't know if it's correct or not, but I got 509
On the row or column?
or row.
509.
Then negative 1, 0, 1, 15, 12, 17.
Okay, I'll wait other people what they have to say. Okay, guys, is this correct or not? I want your help. Yes or no? Okay, Grace 769 in the first row. 769. Okay, 769. So you're saying that this will be 769. Okay, many people got 769. And the second one is -1101. Yes, and 15, 12, 17. Okay. Yeah. Anyway, so you know the idea. You can check it by yourself now. Check it by yourself. Now let's move to another concept. Well, the theorem, okay? Some of the properties of matrix multiplication. Let's go all the way down in your handout. Theorem 2. Let A be M by N matrix, and let B and C have sizes for which the indicated sum and products are defined. Now remember, in order for the sum to exist, the size of the matrix must be the same or equal. And in order for the multiplication to exist, then number of column in the first and number of row in the second matrix must be equal. And let us suppose that they have the size for which the indicated sum and products are defined. Okay. Now, matrix multiplication preserves the associative law of multiplication. So for example, if you have B and C, you multiply B and C first, and then you multiply with A, or if you multiply A and B first, multiply with C, they are equal. You can actually verify easily by some examples, not a big deal. And matrix multiplication with left distributive law. If you distribute this A to B and A to C, then they are equal. You first find the sum of B and C and multiply with A, or you multiply A and B first and add the product of A and C, then you get the same result. Okay, in the same way, right distributive law works in matrix, and scalar multiplication works in matrix, and identity for matrix multiplication. Identity matrix times A will be A. In another word, you know, identity matrix is, let's say, suppose A equals 1, 0, 0, 1. That is the identity matrix for 2 by 2, and we represent that by I2. Okay, this is identity matrix. And if I'm talking about 3 size, I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is called identity matrix of size 3. This is identity matrix of size 2 and identity matrix of size 3. Now, if you multiply, let's say A is, let's say 2, 3, 4, 5, for example, and I is this. So if you multiply A and I2, 2, 3, 4, 5, and if you multiply that with 1, 0, 0, 1, and you should be getting 2, 3, 4, 5. You should be getting that. If you don't trust me, you can actually try this by yourself. Okay, that's what the property part D tells us. Okay, when we multiply by identity matrix, then the matrix preserves its identity. Okay, A will be A. Now, properties above are analogous to properties of real numbers, but not all real number properties corresponds to matrix properties. Keep this in mind. It is not the case that AB always equal to BA. No, that is, sometimes it may happen, but in general, it doesn't work that way. Okay, another important point to remember, warning. If AB, suppose AB equals AC, then can I say B equals C? Does this implies B equals C? Not necessarily. Okay, it may happen sometimes in particular situation, but it is not always the case. In algebra, like when we have xy equals, let's say, xz, then we can write y equals z in algebra. But in matrix multiplication, it doesn't work that way. Okay, if you multiply both sides by a, but just keep that in mind. It is possible for AB equal to 0 even if A not equal to 0 and B not equal to 0. Remember in algebra, high school algebra, suppose if we have xy equals 0, then we can write x equals 0 and y equals 0, right? This implies that. But in case of matrix, it doesn't work that way. Okay, the product of A and B can be 0 without A being 0, without B being 0. Okay, these are some warning because people sometimes try to relate this with their algebra knowledge, and the properties are different in case of matrix. Just keep that in mind. Now let's try this. If A is an n by n matrix and if k is a positive integer, then ak can be written as that way. So for example, A is this, find a cube. How do we find that? Well, a cube means a times a times a equals 1032. 1032. Now you can multiply the first two and then whatever the result you get, you multiply to the other one. Do you want to try quickly, just for fun?
Sir, we get 1, 0 in first row and second row 21 and 8.
Okay, you got 1, 0.
21, 8.
Okay, I'll check with other people. I got same. Okay, Minthia, I got same. Tong, I got same. Okay, same. Sandeep's got the same. Okay. So we got 3 people who agree with your answers, and if we have 2 more, then I assume that that is the right answer because I'm going to use the logic that it's very difficult to get the same wrong answer. If you guys got the same answer, so many people, then it must be right. First, you can multiply this 2, and then you multiply the third one, and finally you should be getting that. Same. Okay, Vivek, same. Anjali, same. Okay, all right, good. Okay, great, guys. No issue there. So matrix multiplication is done. Now, in this section, another concept that we'll be discussing is about transpose. Okay. Here is the example. What is transpose? The definition is if A is m by n, the transpose of A is the n by m matrix, meaning you switch column into row, row into column. That is called transpose. and we represent that transpose by this. In this case, A transpose will be, now you see the horizontal one, you make it vertical. Horizontal 1 to 0, make it vertical 1 to 0. You switch the row into column. The horizontal, this 301, make it vertical, so 301. That is called transpose. Okay. Now you can find B transpose. Switch the vertical into horizontal or horizontal into vertical. So 1, 2, which is horizontal, make it vertical. 0, 1 horizontal, make it vertical. And -2 and 4. That is B transpose. Okay, we're gonna compute this quickly. Now AB. The reason that I want you to practice a lot of multiplication, even though you know how to multiply, but because we need a fluency here. Okay, later on we don't have that much of a time to actually think. You need to be able to, find the multiplication right away. So for that reason, I think if we spend few more minutes in practicing the multiplication, I think it will pay off later.
So we get 1, 4 in the first row.
Okay, just 1 second. And B is 1, 0, -2 and 2, 1, 4. And when you multiply it, tell me, what did you get here again?
1, 4.
In this way?
Yes, sir.
Okay.
And it's 1 and 10 in second row.
1 and 4, and another one is 1 and 10?
Yes, sir.
Okay, this one is, let me see. This one is 2 by 3. This one is 3 by 2. So 3, 3 gone, and it should be 2 by 2. Yes, okay. I will check with other people. Okay. Same, Grace, same. Yeah, Sandeep, Kiran. Okay, so many people got the same answer. Must be the correct one. All right. Okay, now let's try. Okay, this one is done. Now let us find AB transpose. So the second one is AB transpose.
It's 1 and
Horizontal 1, 4
1,
and 1, 10,
10.
right? You just horizontal, write it vertically, and another one that way. And then let us calculate A transpose, B transpose, and we multiply that. A transpose, B transpose. We already calculated A transpose, which is 1, 2, 0, 3, 0, 1. And B transpose is 1, 0, -2, 2, 1, 4. So first, let us check whether the multiplication exists or not. This one is 3 by 2 matrix. This one is 2 by 3 matrix. Yes.
Yes.
Okay, so matrix multiplication exists, and I need your help.
So we got 7,
Okay, 7.
3 and 10 in first row.
Okay.
2, 0, -4.
Mm-hmm.
2, 1, 4.
Okay, I want to check with other people, and let's see. Got the same, got the same. Okay, okay. All right. Thank you so much, guys. So you helped me a lot to find out that answer. Okay. Now, next, what we need to find? B transpose A transpose. So B transpose is 1, 0, -2, 2, 1, 4. That is our B transpose, and A transpose is 1, 2, 0, 3, 0, 1. And now if we multiply, what do we get?
1 and 1 in first row.
1 and 1.
Yes. And 4 and 10 in second row.
I want to check with other people. Okay, so let me check in the chat room what they have to say. Okay, got same. Sandeep, Grace, Kyung, Go, Tong, Sian, CIE. Okay, all of you got the same one. That means it must be correct one. Now, what can we say about AB transpose? Notice here, AB transpose is this. And A transpose, B transpose is this, but B transpose, A transpose is this. Are they same?
Yes.
Okay,
Yes.
so we actually kind of prove one of the theorem experimentally, which tells us that AB transpose equals B transpose A transpose. Okay, we kind of prove it experimentally. That's one of the important relation that you guys need to remember. Okay, AB transpose is not equal to A transpose B transpose. It's not that, but when we transpose, you see the order reverse, B transpose, A transpose. In the same way, here is the theorem. Let A and B denote matrices whose size are appropriate for the following sums and product. A transpose of transpose will be A. I think that is pretty clear, right? It's just a common sense. Here, A transpose means you switch column into row, row into column, and what you do here is that you do the opposite, so you should get the same thing. In case of addition, then A plus B transpose equals A transpose plus B transpose. You can prove this relation by that example. In the previous example, you try that and you can prove it easily. Not a big deal. And for any scalar R, yes, we can do that. It's not a big deal again. And for this transpose, for multiplication, then we just proved this, part D already. AV transpose will be B transpose A transpose, okay? Now, we know this. Now we want to prove this example 6. Prove ABC transpose equals to C transpose B transpose A transpose. Do you want to try that, guys?
Yes, sir.
Theoretical proof maybe. You can start with ABC transpose. That gives me so you can write this as ABC transpose. Maybe I'll use this bracket, not that one, because it will be sometimes confusing with matrix. So maybe I'll use that. Because here when we have 2 items, then yes, we can reverse. Now there are 3 items, but we can actually put them in a 2 item. This is 1 item and this is another, this is 1 matrix and this is another matrix. So what can I say about it? C transpose and AB transpose, right? Because the order now changes. Now in this case, I can use that part D using theorem, part D. We got that again using theorem 3D. Using that theorem, we can say that this will be C transpose and AB transpose is B transpose A transpose. So we proved. Maybe I think I can write one step here and then one more step. C transpose, B transpose, A transpose. So we can extend this not only with for 3 matrices, we can extend this for more than 3 matrices, right? Okay, section 2.1 is done. If you have any question, let me know. Otherwise, we move to section 2.2 for the next like 10 minutes or so, and then we take a break, second break, coffee break. But at this time, we'll be talking about inverse of a matrix in section 2.2. Do you have any questions, by the way, in this section 2.1? Okay, Yang Hui Jiang, sorry if I didn't pronounce your name correctly. What is your question? Yes, okay. Yeah, you can. Yeah, we'll talk it later. Now, let us talk about inverse. In your elementary school, maybe middle school, you know that inverse means, for example, when we have 7 and when we say 7 inverse, it means 1 over 7, right? When you have x inverse, that means 1 over x. But in case of matrix, it has not simply this, it has much more, different than this one. And that's what we're gonna do. It's not like just the reciprocal. This is called the reciprocal, but in case of inverse matrix, this is not simply reciprocal. Okay. Theorem 4, I want you to read this theorem. Let A is a matrix A, B, C, D. It's a random matrix. If AD minus BC not equal to 0, then A is invertible and A inverse is 1 over AD minus BC. This is called determinant, by the way. How do we do that? Well, you multiply crossly, okay? A times D minus C times B. That's how we find. It is called determinant of A. So if we are given a matrix ABCD, 2 by 2 matrix, then A inverse is defined to be 1 over determinant of A, and then what we're gonna do is we switch this D and A. Okay, A is there, D is there, but now we switch the position and we change the sign of this B and C. Okay, that is how we find inverse of 2 by 2 matrix, and that is the definition of inverse matrix for 2 by 2. And for 3 by 3, we'll talk about that after the break. But let us focus our attention on 2 by 2 only now. One thing though, if AD minus BC is equal to 0, then inverse does not exist because 1 over 0 is undefined. So one of the most important condition for a matrix to have inverse is that the determinant should not be 0. Just keep that in mind, okay? A matrix is invertible, or you can find the inverse of a matrix if the determinant is not equal to 0. Just keep that in mind. Now let us look at one simple example. There is solve the system of equation using inverse of the matrix. Okay, let us do this problem. First of all, we want to write this system. You can do this by high school method. I trust you that all of you know how to do it. But here the question is, we want to use the inverse. Okay, using inverse of a matrix, we're going to solve it. Now here is one theorem, keep that in mind. The theorem tells us that If A is an invertible matrix n by n, then for each B in Rn, the equation An, Rn means it's n-dimensional real space. That's what it represents. And we'll talk about this later. Ax equals B has the unique solution. So if we have Ax equals B, then what you can do is you can actually multiply both sides by A inverse, left multiplication, and then you can get A inverse, and A will be I. Okay, Ix equals, I means identity matrix, equals A inverse B. And we already know that if we multiply any matrix with I, it will remain the same, A inverse B. So this is the formula that we'll be using. The proof will do that after the break. But let's work on this example 1. Okay, I want you to write down the matrix in Ax equals B in that form. A means coefficient matrix. Okay, A represent coefficient matrix. So the coefficient matrix will be -7, 3, 5, and -2. X means there are two X. There are X1 and X2. And B means the constant term 2 and 1. So I write the equation in that form, Ax equals B form. Okay. Now we know that this one gives us X equals A inverse B. That's what we found earlier. Okay, that's the formula. So basically we need to find the A inverse in this case. So here this is our A. So now A inverse equals, remember the definition. Okay, if A is, so the definition is here. If A is A, B, C, D, then A inverse will be 1 over determinant, means you multiply that A and D diagonally, AD minus BC, and then you switch the item. D will go there, A will go there, and you change the sign here. This will be -C and this will be -B. So that is the definition of inverse matrix. Okay. So let us find that A inverse here. So in order to find A inverse, we need to find 1 over determinant is -7 times -2 minus BC. So that will be 5 times 3. And then what we need to do is we need to switch this -7 and -2. -2 will become there, -7 will go there. And we change the sign of other two. So that will be -5 and -3. That is our A inverse. This looks ugly. Let us simplify it. 1 over 14 minus 15. How much is that? -1. And that's going to give me -2, -3. What does that mean? Okay, we got A inverse. Any questions so far, guys? Now, the formula is, we know X equals A inverse B. Okay, this is the formula. Equals A inverse is, we already have that, which is 2, 3, 5, 7. And B, we already know. B is this. As you know that this one is your B. So B is 2 and 1. And I want you to multiply and let me know what is the answer.
Seven and 17.
So our x, which is actually, we can write this as x1 and x2. So x1 equals 7 and x2 equals 17. I want to check with other people. Did you get the same answer, 7 and 17?
Yes.
Okay. Let me see. Yes, yes. Okay, same. All right, guys. Thank you so much. Okay, so x1 equals 7, x2 equals 17. You can write in that form, or you can simply write this way. x1 equals 7 and x2 equals 17. You can write that way too. Just in case if you solve this by high school method, you should be getting the same thing. But you know how to check the solution, right? If you substitute this value in this equations, and I think the equation will satisfy. So that's how we can check. And yeah, we can use this inverse to solve the system of equation. Okay, guys. Now, if you have any question, let me know. Otherwise, we take another 10-minute coffee break. Okay, theorem 5 is if A is an invertible n by n matrix, remember this is a square matrix. In general, you know, invertible matrix are a square matrix in general. So then for each B in Rn, the equation Ax equals B has the unique solution. Okay, there is only one solution exists. What it means is, for example, in our previous case, example 1, the solution that we got x1 equals 7, x2 equal to 17, that is the only solution for that system. Okay, and this solution is unique, means there is, you know, this is the unique solutions, and we want to prove this here theoretically. Okay, let us assume that A is any invertible matrix. If it is not invertible, then we cannot find inverse matrix. So this theorem does not apply in that case. Assume that A is any invertible matrix. Then we need to solve. We want to solve for Ax equals B. That's what we want to solve, right? So then that means if multiplying both sides by, I can write this, A inverse Ax equals A inverse B. I can write that left multiplication by A inverse. If you multiply on the right side, it's not going to work. So you must multiply on the left side. That's why I write it down here. Left multiplication by A inverse gives us this. Now A inverse and A, we know that that is I, unit matrix. Okay. So when you do A inverse and A, we got Ix equals A inverse B. So if we multiply any matrix with the identity matrix, we simply get the same matrix, X equals A inverse B. Okay, we solve this for X. Now, the question is, it has a unique solution. So we need to prove that this is unique. Okay, there is no other solution exist. This is the only solution for that system. That's what we want to prove. Okay, how to prove that? Well, what we do is, let us suppose that there exists another solution. Let us suppose that y is, let's say, another solution. Also a solution for the given system, okay, for ax equals b. Let us suppose that y is also the solution for this. Then what we can write is, we can write that ay equals b. If y is the solution, then we can write that. Now we multiply as we did before, A inverse ay equals A inverse b. So what we did here is that left multiplication by A inverse. We can do that. So this part will be Iy equals A inverse b, and that gives me y equals, because when I multiply this by I, it will remain the same, y equals A inverse b. Now notice that we assume y is a different solution. That's what we assume. But at the end of the day, what we got is the same thing as we got for x, right? Which is exactly the same solution. We got for x, right? So the solution is unique. So the solution is unique. Okay, that's how we can prove it. Any question? Okay, so if there is no question, then we will move to how to find. Okay, yeah. So now let us look at theorem very quickly, and then we will learn how to find the inverse of 3 by 3 matrix. Okay, first let us look at this theorem. Suppose A and B are invertible, then the following results holds. A inverse is invertible, and A inverse will be the same thing. Keep that in mind. Inverse of A inverse will be A. If A is invertible and AB inverse equals, then AB inverse equals B inverse A inverse. You see the order actually changes here. And part C, A transpose is invertible and A transpose inverse equals A inverse and transpose. Let us quickly prove this part B. Part A is obvious, part C is also pretty obvious, and let us prove that part B right now. Okay, we just need proof for the part B only. AB inverse is B inverse A inverse. If we want to prove that, okay, what we need to prove here is in part B, we need to prove inverse of AB, which is AB inverse equals B inverse A inverse. That's we need to prove here. So in another word, we need to prove that AB and B inverse A inverse should equals to I. If we prove that, then we are done with this one. Okay, consider this now. Now our goal is to prove that this equals I. Let us check that whether it is true or not. As you know that matrix multiplication is associative. I need a little more space here. I'm gonna go there, okay? Just give me 1 second. So we want to consider AB and B inverse A inverse. Consider that since matrix multiplication is associative. Associative means we can put them in a different group. Okay, if I like, I can write down that A, B, B inverse, and A inverse. I can write that way too. Okay, associative we can write this way. Now this gives me A, B, B inverse will be I. We know that. A inverse. And now A times I. When we multiply with the identity matrix, it preserves the same matrix. So it will be A and A inverse. And A inverse is I. Therefore, we can say that AB inverse equals B inverse A inverse. Okay, proved. Any question, guys? And this rule can you quickly tell me, suppose this can be extended for more than 2 matrices. For example, if I have A, B, C inverse, what does that mean? According to that property, we can write this as C inverse,
B inverse,
B inverse, A inverse, okay? And this is also true. So we can extend this more than 2 matrices. Just keep that in mind. For transpose as well as for inverse, the position will reverse. Okay, with this theorem, and we quickly learn one thing here, that is one definition, elementary matrix. What is elementary matrix? Well, an elementary matrix is one that is obtained by performing a single elementary row operation on any identity matrix. For example, this one is 3. You know that 3 by 3 identity matrix is, we know 3 by I3, which is 3 by 3 identity matrix, 1 0 0 0 1 0 0 0 1. So elementary matrix means it is one that is obtained by performing a single elementary row operation. So now look at this E1. How can you get E1 from I3? You can do only one operation, only one steps that you can do. How can you get that from here to there? What is that? What is going on with E1?
Multiply row 2 by 2.
Okay, 2I3 gives me E1, right? Well, not 2I3, so R2. Just multiply R2 by 2, and then you're gonna get 1 0 0 0 2 0 0 0 1. So what we did, this is actually E1. So what we did is we just did one operation only in the identity matrix. So if you do only one operation, you are not allowed to do more than one. If you do only one operation and then you get that, that is called elementary matrix, by the way. Can you tell me how do you get this one from I3? What is done with that one from here to here? What is that?
swap row 1 and swap row 2 and row 3.
Exactly. You just swap row 1, row 2 and row 3 and you get that. Okay. So just one operation we did. So that kind of matrix are called elementary matrix. Okay. Just keep that in mind. In the same way, you can figure that out yourself. Now, another important concept for this section 2.2 is how to find the inverse of the matrix which is more than 2 by 2 size. How to find the inverse of 3 by 3 matrix, 4 by 4 matrix. Remember, in general, for inverse to exist, it must be a square matrix, okay? So what we do is we'll try this example 3 together, and I'll give you one example for you to work on your own just for fun, and then we'll be done with this section and we move to the another section. Let's work on that. So the previous method that we learned for 2 by 2 doesn't work here. Okay, we have to do a different, we need to do it different way. Okay, so consider, in order to find the inverse for 3 by 3 or 4 by 4 or 5 by 5, consider always the A and I, this matrix. Consider that. Which means A is 0, 1, 0, 1, 0, 3, 4, minus 3, 8. And I means it is 3 by 3i, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, this is our matrix. Now, the whole idea is to change is to convert left part of the matrix into identity matrix. And then whatever is left on the right hand side, that will be the inverse, and we'll verify that. So our goal is to change the left hand side, left part means this part right here, into identity matrix. Okay guys, use the use the same process that you did in changing into echelon form, and try to change this left part of the matrix, left part from this line, this part, into identity. You change this into that form. So what do you want to do first? We don't want that 0, we want 1. So maybe you want to try
Change
R1 plus R2.
Switch the
R1 to R2.
row 2 to row 1.
yes, yeah, swap R1 and R2. You're not allowed to do in the column, okay? All this row operation, keep that in mind. I have been telling that from lesson 1. We are doing row operation only. We'll do a column operation in determinant in the next chapter, but until now, you're not allowed to do the column operation. We are doing all the row operation. Okay, then you're gonna get 1, 0, 3, 0, 1, 0. You need to, you need to change the whole thing on the right hand side as well. And 0, 1, 0, 1, 0, 0. And we did nothing with the third one, so 4 minus 3, 8, 0, 0, 1. Okay, now make this guy 0. Okay, make
R3.
0. So how can you do that?
R3 minus 4R1.
In R3, we'll do R3 minus 4R1. Okay, good. R3 minus 4. R3 is negative 3 minus, there will be negative 3. R3 is 8 minus 4, 12. Is that minus 4?
Yes.
And then R3 minus, that will be 0. R3 minus 4. So that will be minus 4. And that will be 1. Now, you need to make this guy 0.
Operate R3 plus 3R2.
3R2.
Yes, okay. In R3,
R3 plus 3R2.
okay, thank you. R3 plus 3R2. R3 plus 3R2.
I think it's 0.
Which one?
The 3 minus 4. The 3 one is a 0.
Okay, let me see. This is 0. This is 0. And R3 minus 3R2, that will be negative 4.
Yeah,
R,
after that, it's
R,
not a 3, it's 0, I think.
R3 is 0 plus 3R2. 0 plus 3 is 3, isn't it? And minus 4 R3 plus,
Yeah, it's right.
yeah?
Yeah.
R3 plus 3R2 is that one. Okay. Now you want to make this 1. Make it 1.
Divided by minus 4.
Yes, exactly. All right. R3 divided by negative 4. It's a lot of work, but not difficult, right?
Where you read? Oh, it's fine. It's fine. Sorry.
Good.
3 over 4, negative 4, by the way. This will be 1, and this will be negative 1 over 4. We are almost there. Now we need to make this guy 0.
R1 minus 3R3.
In R1 minus,
3R3.
thank you. So you're gonna get 1, 0, 0.
0, 1, 0.
R1 minus 3 means that will be, how much is that? 9, negative 9, I mean positive 9 over, this will be 0, minus plus 9 over 4, is that right?
Yeah, 9 over 4.
Okay, and that guy will be R1 minus 3. Is that
Minus 3.
negative 2?
Yeah.
This minus negative positive 3 over 4. And we did nothing here. 0, 1, 0, 1, 0, 0, and 0, 0, 1, negative 3 over 4, and 1 and negative 1 over
Minus
4.
1, 4.
Okay, that's what we got.
Yeah, we also did this one in high school.
Yeah, okay. Okay, all right. All of you got the same thing?
Yes.
Sometimes in this situation, if you don't pay attention, then there may be a chance to mess up with addition and subtraction of the numbers, right? So make sure that we are on the same page. Okay. Now, so the inverse is, let me write it here. So the inverse is So A inverse is on the right hand side of the matrix, which is 9/4, 1 and -3/4, -2, 0, 1, 3/4, 0, -1/4. That's what we got. Now, how to check whether this is right or wrong?
Multiply with the identity function, no, in the I matrix.
Okay, let us check that. Okay, let us check. What we know is that when we multiply A and A inverse, then this must be I. Okay, let us multiply that. A is there and A inverse is 9/4, -2, 3/4, 1, 0, 0, and -3/4, 1, -1/4. And A is, what is A by the way? And this is 0, 1, 0, 1, 0, 3, 0, 1, 0, 1, 0, 3, 4 minus 3, 8. 4 minus 3, 8. Okay, can you please multiply and let me know whether you get I?
Yes, sir, we get the I.
Right? You got that? Okay, so it checks, right? So our answer is correct. That's how we can check. Okay, section 2.2 is done actually. You'll be able to solve all the homework questions from this section 2.2. Now, if you have any questions, let me know. Otherwise, we move to another section 2.3. In 2.3, we don't do much. We just, there is only one theorem. In 2.3, we just attend that, we just read that theorem and couple of conditions, couple of properties of matrix we'll look into, and that's it from section 2.3. So there is no homework from section 2.3, by the way. The reason that I just want to attend that section 2.3 right now is because this theorem will use later in chapter 4. And I can tell at that time that, okay, that's what we did in chapter 2. So for that reason, I'm going to now section 2.3, which is called characterization of invertible matrix. Invertible matrix means we already know that the matrix whose inverse exists. We call it invertible matrix. Okay. If the inverse does not exist, then we call it non-invertible or singular matrix in that time. At that time, sometimes this is called non-singular matrix as well for invertible. We'll discuss that later. The invertible matrix theorem. I want you to read this. Okay, just pay attention to the one that I highlighted with red ink. Other part we'll discuss in chapter 4. Let A be a square n by n matrix, then the following statements are equivalent. Meaning if A is invertible, then if one statement is true, then all of these statements are true. If one statement is false, then all of them are false. Okay, that's what it is saying. Now suppose if A is invertible, then A has n pivot position. A transpose is also an invertible matrix. If A is invertible, then A transpose is also invertible. And then I'm gonna add one more property here, Ij, that determinant of A not equal to 0. And we already know how to find the determinant of 2 by 2 matrix, but for larger size of the matrix, we'll learn how to find determinant in chapter 3. But just keep in mind that if A is invertible means in order for the inverse to exist, determinant should not be 0. Okay. And the last questions for today's class is use the invertible matrix theorem to decide if A is invertible where A equals this one. So now you can use any theorem. You can use either J, you find the determinant of this, and we will learn how to find determinant in our next class. That's one way. Or you can use this pivot, okay? Change it into echelon form and see how many pivot it has. So you can do a couple of ways. So we have about 5 minutes. Can you change it into echelon form? Change to echelon form. And once you change it into echelon form, you will notice whether there, how many pivot positions are there. Okay. So when you change it into echelon form, then I think you're gonna get. I trust you guys. You can change it into echelon form, and let me just directly write down using my software, online calculator, and that changes this matrix to the echelon form for me right away. And now I already got the echelon form of that, but you know how to change it into echelon form. 1, 0, -2, 0, 1, 4, and 0, 0, 3. That's what I got. Now tell me what are the pivot here. So there is one pivot, and once you have taken this pivot, then you cannot take any other pivot in that row. This is gone. This is gone. There is another pivot. Now this is gone. This is gone. There is another pivot. How many pivot are there?
3.
3 pivot positions. Okay, clearly there are 3 pivot position. Remember, A is what? A is the size of the A is 3 by 3, right? Size of A is 3 by 3. So this is n by n. Remember here, n by n matrix. So n by n. So that means n equals. So n equals 3. And here also you got n equals 3. So they are equal. So that means inverse exists. That's how we can figure out whether inverse exists or not. Okay, A is invertible. And how to find the inverse? The same process that we just did.
Sir, could you just explain? I didn't understand from last chapter. Pivot position, pivot row, pivot position, and basic variables and free variable. Just those from this matrix. If you could explain.
Well, I cannot explain in this 2-3 minutes now. This is what we spend like almost like 3 hours on those concepts only. But what I can do is maybe during the office hour, I'll have a little bit more time now because my another class is about to come. I have now 3 minutes with me. I cannot explain all those concepts right now. Maybe tomorrow in the office hour. Is that Vivek?
Yes, yes, sir.
Yes.
So what
Vivek.
time is the office hour at?
9:30.
9:30.
Yeah, I will. I'll keep the office hour open at. I may be late, maybe like 10 minutes,
Okay,
but I'll be there around 9:40 for sure.
okay, sir.
Okay.
Yes,
And you can go into my office hours again from the canvas.
yes. Okay, thank you.
Okay. So to check whether the matrix is invertible or not, you don't have to do the long process like we did here. Okay, you can just change it into echelon form and figure out whether number of pivot and then this n are equal or not. But if you need to find the inverse, then you have to do all these steps, right, that we did. Okay, this much for today. If you have any questions, then let me know. Otherwise, I need to say goodbye. And remember, there will be a quiz in Canvas in our next class, and detailed information has already been uploaded, posted there.
Do we have chapter 2 in the quiz?